Welcome viewers. Today we'll see the Coulombs law. The Coulomb states that the electric charges produce the mechanical force on each other. If the two charges are placed at a distance, then force will be developed on each other. The expression for this force and characteristics was given by the Coulombs law. First we'll see the characteristics. The like charges repel each other, but unlike charges attract each other. First point. Second one, the force is proportional to the product of the magnitude of the charges. If the two charges are available, mean the force will be proportional to Q1 and Q2. The third point, the force is inversely proportional to square of the distance between the two charges. 1 divided by r square, right? Inversely proportional to square of the distance between the charges. The force depends upon the medium in which the charges are located. Where the charge is located depends upon the medium it will act. And the last one is the force is always act along the straight line joining the 2 point charges. It will always act along the straight line. So these 5 points are given by the Coulombs, these 5 characteristics. Based on that we can go for the derivation. We'll see the diagram. So there are two charges available, Q1 and Q2. Q1 is placed at point 1, Q2 is placed at point 2. This R12 is the distance vector between Q1 and Q2. A12 is the unit vector. This F1 is the force developed on the charge 1 due to second charge. Similarly, the F2 is the force developed on Q2 due to the first charge. See the direction, both are equal but in opposite direction, right? So the expression for this force will be given by the Coulombs. Before that we'll see the unit vector. Unit vector is nothing but vector by scalar. The general formula is vector by scalar. It can be expressed in two ways, in terms of force or in terms of distance vector. In terms of force mean this F2 vector by F2. Vector by scalar. This is magnitude of F2. In terms of the distance vector, A12 vector equal to R12 vector. Now this charge Q1 and Q2 are separated by the distance R12. What we need? Two charges Q1 and Q2. The distance between the charges R12. So based on the diagram and based on the characteristics given by the Coulombs, it is that the force is directly proportional to product of magnitude of the charges Q1 and Q2. Similarly, inversely proportional to square of the distance between the charges. So F2 is directly proportional to Q1 Q2 divided by R12 square. This is based on the X point given by the Coulombs. So while equating, we need to introduce one constant, 1 divided by 4 pi epsilon. Q1 Q2 divided by R12 square. What is this epsilon? Epsilon is the permittivity. What is permittivity? The electrical energy storage is given by the permittivity. The factor given by permittivity is nothing but electrical storage of the any medium. That is epsilon naught and epsilon r. What is epsilon naught? Absolute permittivity. That will be constant, 8.854 into 10 to the power minus 12. Epsilon r is relative permittivity. That is depends upon the medium, right? So epsilon equal to epsilon naught, epsilon r. Epsilon naught means absolute permittivity, that will be 8.854 into 10 to the power minus 12. Epsilon r is relative permittivity, that is depends upon the medium, right? Now this F2 is nothing but is a scalar form. We will take this as equation 1 in a scalar form. In order to get the vector form, we can refer the unit vector. A12 unit vector equal to F2 vector by F2. Right. So cross multiply this so that A12 unit vector into F2 equal to F2 vector. Right. So this F2 vector can be written as A12 vector into F2. Now we can get the scalar vector form, F12 equal to A12 into F2. What is this? F2 is already available in equation 1. So from equation 1 we can substitute the value F2 equal to, this is nothing but now vector. Previously what we calculated is scalar. 1 divided by 4 pi epsilon q1 q2 divided by r12 square into a12 vector, a12 unit vector. Now it is in a vector form, but a12 in another form is r12 vector by r12 in terms of distance vector. So we can replace this a12 by r12 vector by r12. So finally what we got, f2 vector equal to q1 q2 divided by 4 pi epsilon r12 cube into r12 vector. This equation number 2 is completely the vector form. Equation 1 is the scalar form. The value of epsilon, permittivity, epsilon naught into epsilon r. Epsilon naught is absolute permittivity, 8.854 into 10 to the power minus 12. This relative permittivity based on the medium will take this a free space. For free space it will be 1, right? So this 8.854 into 10 to the power minus 12 into 1. For simplification I can write it as 1 divided by 36 pi into 10 to the power 9. Both are same only. For a simplification it is given in terms of pi. 1 divided by 36 pi into 10 to the power 9. Now we'll substitute this epsilon value in the second equation, vector form. So q1 q2 divided by 4 pi epsilon r12 cube into r12 is nothing but the scale vector form, equation number 2. In this we are going to substitute this epsilon value. So q1 q2 divided by 4 pi into 1 divided by 36 pi into 10 to the power 9. This value, this epsilon value is substituted, and r12 cube into r12 vector. So this can got cancelled, 4 pi and this 36 pi. So it got 9 times. So 9 into 10 to the power 9 available in the denominator. So it will go to the numerator. So 9 into 10 to the power 9. What is, by cancelling these two, here 9 will be there. 9 into 10 to the power 9 will go to numerator. So 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector, right? So this is nothing but force developed on the second charge f2 in a vector form. 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. That equation 1 is the scalar form, q1 q2 divided by 4 pi epsilon r12 square, that is a scalar form. So while using the problem or while solving the problem based on the vector quantity or scalar quantity, whether we can use equation 1 or this equation. This is a scalar form or vector form. This is a vector form that can be used while solving the problem. Based on the data available, either we can go for vector form or scalar form, right? Then what about the F1, first force F1? We calculate, we got the expression for F2. What about F1? Both are equal and opposite. So F1 vector equal to minus F2 vector, right? Because of both are equal and opposite, the F1 can be expressed as minus of F2. 50 microcoulomb and Q2 10 microcoulomb. Located at the point minus 1, 1, minus 3 and 3, 1, 0. Find the force on Q1, right? Two charges available, 50 microcoulomb and 10 microcoulomb at two different points. We need to find what is the force on the Q1. The diagram is available here, right? So this is Q1 at located at first point minus 1, 1, minus 3. Q2 available at second point 3, 1, 0. It can be written as x1, y1, z1. Similarly, x2, y2, z2. So this r12 is the distance between the distance vector. What is the formula for this? 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. We can use the vector form because the 2 points are available. Easily we can calculate the distance vector, so that we can use the vector form, right? So 9 into 10 to the power 9, q1 q2 values are already available. Q1 is 50 microcoulomb, that is 50 into 10 to the power minus 6 coulomb. Q2 is 10 microcoulomb, that is 10 into 10 to the power minus 6 coulomb. What we need is r12 vector and r12 the magnitude. We need this r12 vector, right? So other terms are already available. How will you find this r12 vector? Distance vector. R12 vector is nothing but distance vector. distance between the 2 points, very easy. Here we have x1 y1 z1, x2 y2 z2. So r12 vector can be calculated as x1 minus x2, distance vector, difference between the distance, x1 minus x2 into I vector plus y1 minus y2 into j vector plus z1 minus z2 into k vector. Right, now we can substitute the value. X1 is minus 1, x2 is minus 3, y1 is 1, y2 also 1, z1 is minus 3 and z2 is 0. So minus 1 minus 3, it becomes minus 4i. 1 minus 1 0, so 0j minus 3k. Right, so finally what we have, minus 4i vector minus 3k vector. Now we got the expression for r12 vector, minus 4i vector minus 3k vector. So this is the distance vector. How will you find the magnitude? Square root of this coefficients, right? Square root of minus 4 square plus minus 3 square, that is nothing but equal to square root of 16 plus 9, that is square root of 25, it is equal to 5. Right, now we got the magnitude also. Right, the r12 vector also calculated, r12 magnitude also calculated. Now we can substitute in the formula. This f1 vector equal to 9 into 10 to the power 9 q1 q2 divided by r12 cube into r12 vector. Now we can substitute the value. 9 into 10 to the power 9, q1 is 50 into 10 to the power minus 6, q2 is 10 into 10 to the power minus 6 divided by this magnitude is 5 cube. Right, the vector is minus 4i minus 3k, j is not available, j is 0. Right, by simplifying this, what we got, 0.036, simplification of this term is 0.036. Then this vector minus 4i vector minus 3k vector, you can multiply inside, so that what we got, minus 0.144 I vector minus 0.108 k vector. Right, now we got the vector in the force F2 in a vector form, right, because the 2 points are given, so we can use the. Right, we'll go to the second problem. The second problem is, there is a triangle is available. At each corner of the triangle, the charges are placed. This is the first corner, second corner and third corner. In each corner, the charges are placed are equal value, 0.25 microcoulomb. Here also 0.25 microcoulomb. The distance also 0.1. It means it is a equilateral triangle. So that angle will be 60 degree. Right, at 3 corners of equilateral triangle, 3 charges are placed. The charges value are equal. The distance also equal. Due to equilateral triangle, it is 60 degree. What is the question? Determine the force on any one of the charge of the configuration shown in diagram. We need to consider one charge. For that, we need to find the force on that charge due to second and third charge. Okay. We will consider this first charge. We will see what is the force on the first charge due to second charge and third charge. Right, we will consider the first charge due to the second charge. What is the force on first charge? Due to the third charge, what is the force on first charge? Right, first we will see first and second charge. So there is a force exists between first and second charge, that is nothing but F12. F12 is the force on the first charge due to second charge. Both are available in the same line. The angle between these two is 0. So we have only one component, that is called horizontal component. Right. Next we will see the force between 1 and 3, that is F13. F13 is the force on the first charge due to third charge, F13. But first charge and third charge is placed at an angle of 60 degree. So what will happen? This F13 will be resolved into two components, horizontal component and vertical component. Right. How will you find this horizontal component? That is nothing but total component multiplied by cos of theta is horizontal component, F13 cos 60. What about vertical component? Total component multiplied by cos of theta is the vertical component. We can easily remember F13 sin 60. Right. So horizontal component is total component multiplied by cos of theta. Vertical component is total component multiplied by sin of theta. Now we have three different components available: F12, F13 sin 60, F13 cos 60. Right? These two are horizontal components. From the diagram itself, we can easily understand that F12, F13 cos theta are horizontal. This is the only vertical component, F13 cos 60. Right? Now we'll find this value one by one. The important thing is here the charges are equal, Q1 equal to Q2 equal to Q3, that is equal to Q. So that the forces also equal, F12 equal to F13, that is equal to F. Because charges are equal and the distance also equal. So the force between the charges will be equal. Q1 Q2 divided by 4 pi epsilon r square. Right? Here we are using the scalar form. Previous problem we used the vector form. Here the scalar form. Q1 is 0.25 into 10 to the power minus 6. Q2 also same, 0.25 10 to the power minus 6. Right? 4 pi epsilon naught value is 8.854 into 10 to the power minus 12. Right? The medium is not given, mean epsilon r will be 1. We will take it as a air medium. Right? Then the distance is 0.1. Right? 0.1 square. So what we got? 0.056 Newton. Right? Whether it is horizontal or vertical component, due to equal charge and equal distance, the force between is 0.06 Newton. Right? Now we'll find the components one by one. So F12 is the force experienced by Q1 because of Q2. F13 is the force experienced by Q1 because of Q3. That already we discussed. Right. Now we'll see the horizontal component. There are two horizontal components, F12 plus F13 cos theta. Right? F12 and F3 both are equal. We can substitute 0.056 plus 0.056 into cos 60 will be 1 by 2. So it will be 0.084 Newton, horizontal component. What is vertical component? F13 sin theta. 0.056 into sin 60 is root 3 by 2. So it is 0.04849 Newton. Right? So now we got the horizontal component and vertical component. Then we can find the total force. That is nothing but square root of Fh square plus Fe square. Right? By substituting the value, we got 0.097 Newton. Right? So finally what we got? 0.097 Newton. Right? I will explain again. So this F12 is the force on first charge due to the second. Only horizontal. There is no vertical because both are available in the same line. F13 is the force on first charge due to third, but it is available at an angle of 60 degrees. So it is resolved into horizontal component and vertical component. So that we are treated these two are horizontal. This is the vertical. We calculated this force one by one. This force value will be equal, that already calculated, 0.056. From this we can calculate the total force, 0.097 Newton. The distance and force between the charges. We can easily calculate what is the distance between the charges and what is the force between the charges. Then electric field can be calculated. That is the important thing. Electric field can be calculated from the Coulombs law. But what are the limitations available? The law is applicable only for point charges at rest. It is applicable only for the point charges. Then inverse square law is applicable. We are using 1 divided by R12 square. Right? Similarly, charges are arbitrary shape. Right? That is normally it is a sphere. From that what we can understand what is the important point. Coulombs law is an implication of Gauss law. From Gauss law we are deriving the Coulombs law. The direction of force is always from positive charge to negative charge. This is a very common point, you already know. Always the force will start from positive charge and towards the negative charge. Coulombs law employed in electrostatic, only in the static field. Coulomb is the unit of charge. Because of Coulombs law, we are referring the charge unit of the charge as Coulomb. Right? So in this video, we discussed about the Coulombs law, what are the characteristics and how to get the derivation expression for force, and we solved two problems. One is based on scalar, one is based on vector. Then we discussed the application, limitation and important points. Thank you for your cooperation. Welcome viewers. Today we'll see the electric field intensity followed by the electric field intensity due to finite charged wire. First we'll see the definition of electric field intensity. The electric field intensity is nothing but force per unit charge, F divided by Q. That is, the electric field intensity at a point is defined as the force per unit charge on a test charge being as small as possible in comparison with the other charges forming the system. So the general formula for the electric field intensity is F divided by Q. We can refer this diagram. We have one charge is available placed at the origin, capital Q, and another charge, small q, placed at a distance r meter from the origin at point A. This UR is the unit vector. So we have one force, one charge at origin, another charge at a distance r meter at a point A. So due to these two charges, the force will be created. That force is given by, based on the Coulombs law. The force is given by Q into capital Q into small q divided by 4 pi epsilon r square. That r is nothing but distance between the charges. So bring this q in the denominator, so that we got q divided by 4 pi epsilon r square. So this F by Q is nothing but electric field intensity. So that is E equal to Q divided by 4 pi epsilon r square. So this is the general formula, electric field intensity, Q divided by 4 pi epsilon r square, right? So in this derivation, we are going to start with this basic equation, E equal to Q divided by 4 pi epsilon r square. Before starting the derivation, we will see the charge distribution. What are the charge distributions are available? So there are three type of charges available. Charge density, linear charge density, lambda dq by dl, that is divided by length. Then it is called as a linear or line charge density by considering only the line. The unit is coulomb per meter, right? If we consider the area, then it is called a surface charge density, sigma dq divided by ds. Here we are considering the surface area, coulomb per meter square. If we consider the volume, then it is called a volume charge density, rho dq divided by dv, coulomb per meter cube, right? So in the density, we have three types available. Linear density means length, surface charge density means area, volume charge density means volume, right? So we have lambda, sigma and rho. Based on that, we have the derivation. Now we'll see the electric field intensity due to a finite charged wire. One finite charged wire is there. In that, we are going to obtain the expression for what is the electric field intensity, right? You can refer this diagram. So this is a finite charged wire, AB. Finite charged wire, it is termed as AB. So this is the point P. At this point only we are going to find the electric field intensity due to this charged wire, right? So the distance between this point P and the midpoint or origin is d meters, right? This finite charged wire is assumed with a lot of charges. Point charges are available. N number of point charges are available in the finite charged wire. In that we assumed only one charge, right? So that the details available here. Lambda equal to dq by dl. Because of length, there is a finite charged wire, we are assuming the linear charge density dq by dl, lambda. From that we can find here the L is replaced by x. Due to the x, we are considering x, so that dq divided by dx, that is, to cross multiply this, dq equal to lambda into dx. So the small charge available at this point is represented as lambda into dx, that is linear charge density into small distance dx. Like that, there are n number of charges available. For the calculation purpose, we consider only one charge at a distance x meter, that can be represented as lambda into dx. So the distance between this point charge and point P is r meter, right? So this triangle is drawn separately here for calculation purpose, and dxr is drawn separately. This is the theta, angle theta. For calculation purpose, it is drawn separately. So this is the theta, this angle will be 90, means automatically this remaining angle will be 90 minus theta, right? So due to the point charge, we have the electric field intensity is produced on the opposite side, dE. For any point, if it is inclined, the total electric field intensity will be divided into horizontal component and vertical component, DEH and DEB. If any point is there, that will be resolved into horizontal and vertical component, right? So this angle is 90 minus theta, mean automatically this angle will be 90 minus theta, right? So this triangle, in order to find the horizontal and vertical component, this triangle is drawn separately here, right? So this is the horizontal component, this one. This will be total component, this one. This will be vertical component, DEH, DEB and DE. And the angle will be 90 minus theta. So from this we can find the what is the expression for horizontal component and what is the expression for vertical component. How will you find? You find the expression for cos 90 minus theta. Cos 90 minus theta means, cos theta means adjacent side by hypotenuse. What is adjacent side? DEH divided by DE. Cos 90 minus theta is nothing but adjacent side by hypotenuse. Adjacent side is DEH, hypotenuse is DE. You cross multiply this, so that DEH equal to DE cos 90 minus theta. So you can simply remember horizontal component equal to total component multiplied by cos of theta, right? For anywhere we can use that. The horizontal component equal to total component multiplied by cos of theta. Similarly, we can find sin 90 minus theta. Sin theta means, sin 90 minus theta means opposite side by hypotenuse. Opposite side is DEV, hypotenuse DE. So DEV by DE equals is given by sin 90 minus theta. You cross multiply this, so that DEV equal to DE sin 90 minus theta. So vertical component equal to total component multiplied by sin 90 minus theta, right? Now we got the expression for horizontal component as well as vertical component. From that we can find the total component also, right? So in this diagram, this for point A, the wire is named as AB. The equivalent angle will be alpha for A. For B, equivalent angle will be beta, right? During the limit, while substituting the limit, we can refer this angle alpha and beta equivalent to A and B, right? So that description is given here. The wire is uniformly charged with a charge density lambda coulomb per meter. The wire is assumed to be formed by several point charges. In that we consider only one point charge at a distance x meter, right? So the DE is the small electric field intensity due to the small charge. R is the distance between the charge dq and point P, right? The detail about the diagram is given. Now we'll see the electric field intensity, right? The general formula just now we discussed, E equal to Q divided by 4 pi epsilon R square. That is the general formula for electric field intensity, right? We consider the small charge dq, so that the electric field intensity also small, dE. Further we can go for integration. At that time we will get the total electric field intensity, so that E become dE, Q become dq divided by 4 pi epsilon R square. But dq is given as lambda into dx in terms of linear charge density. So dE equal to lambda dx divided by 4 pi epsilon R square, right? So after substituting these values, right, the lambda, we got this value. You take it, this is a equation number 1. Right, now what we are going to do, we are going to find the dx and r value from this triangle, right? Dx and r from this triangle. This triangle already we discussed, right? In this triangle, this is x, d and r, this is a theta. Find the expression for tan theta. Tan theta means what is that? Opposite side by adjacent side, d by x. Opposite side by adjacent side, d by x, right? You exchange this value. So x equal to d by tan theta. 1 divided by tan theta is cot theta, right? So x equal to d cot theta. But here what we need is dx. So differentiate on both the side. Dx equal to differentiation of d cot theta. So differentiation of this d is taken outside. Differentiation of cot theta is minus cosecant square theta d theta. Differentiation of cot theta is minus cosecant square theta into d theta. Therefore dx equal to minus d cosecant square theta into d theta. Right. Similarly, find the sin theta. Sin theta means opposite side by hypotenuse, d divided by r. Opposite side by hypotenuse, d divided by r. Cross multiply this. So r equal to d by sin theta. 1 by sin theta is cosecant theta. So r equal to d cosecant theta. Now we got the expression for dx and r. So these two can be substituted in equation number 1. Right, now substitute this value. This is the equation 1, lambda dx divided by 4 pi epsilon r square. In the lambda into substitute dx. Dx is minus d cosecant square theta into d theta divided by 4 pi epsilon. R is nothing but d cosecant theta. So r square means d square cosecant square theta. So this cosecant square theta got cancelled. 1d got cancelled, right? So the negative symbol is available. So minus lambda d theta, this d theta divided by 4 pi epsilon d. Right, now we got the expression for electric field intensity, small electric field intensity, minus lambda d theta divided by 4 pi epsilon d. We will take this is equation number 2. Right, we already discussed we have horizontal component and vertical component. First we will find the horizontal component, right? What is horizontal component? Horizontal component equal to total component multiplied by cos 90 minus theta. From the triangle we already got this expression. So cos 90 minus theta can be written as sin theta. Cos 90 minus theta is nothing but sin theta. So deh equal to de sin theta. We got this value dE. From equation 2 we have this dE value. So we are going to substitute this dE value from equation number 2, right? So that dEh equal to minus lambda 4 pi epsilon d, the sin theta is there, sin theta into d theta, right? Minus lambda divided by 4 pi epsilon d sin theta d theta. So this is nothing but a small electric field intensity, horizontal component. By integrating on both the side, we will get the total electric field intensity. So we can go for integration. Minus lambda divided by 4 pi epsilon d sin theta d theta. What is the limit for the integration? That is very important. The limit is nothing but we need to consider the entire length of the cable, AB. AB is the length of the cable. But integration is with respect to theta. So that we are taking alpha and beta. Equivalent for point A, the equivalent angle is alpha. Point B, the equivalent angle will be beta. So that we are taking beta to alpha. Right? It is clear. So for length, instead of length, we are taking the angle because the integration is with respect to theta. Right. Now we'll go with the integral dEh is nothing but EH minus lambda divided by 4 pi epsilon d is constant. Only we need to integrate sin theta d theta with a limit beta to alpha. Right. So minus lambda divided by 4 pi epsilon d, the integral sin theta is minus cos theta with a limit beta to alpha. You substitute the limit minus cos alpha. While substituting lower limit, one negative will be there, already one negative is there, so it becomes positive cos beta. right? So you multiply inside this negative so that this become positive, cos alpha minus cos beta, lambda divided by 4 pi epsilon d cos alpha minus cos beta. So this is the horizontal component. We got the expression for horizontal component. Now we'll see the vertical component. Vertical component is given by DEV equal to DE sin 90 minus theta, sin of theta. Sin 90 minus theta can be written as cos theta. So DEV equal to DE cos theta, right? Now we can substitute the DE value from equation number 2. Equation number 2 we have DE value, so that DEV equal to, this DE is nothing but minus lambda divided by 4 pi epsilon d cos theta into d theta. Right. This is for small value. By integrating on both the side, we will get total vertical component, right? So it is integrated. The limit is beta to alpha. We already discussed the limit will be beta to alpha. So integral DE is nothing but EV. So this will be EV, vertical component, equal to minus lambda divided by 4 pi epsilon d integral beta to alpha cos theta into d theta. These are all constant. Only we need to integrate cos theta, right? So that minus lambda divided by 4 pi epsilon d, this integral cos theta is sin theta. We need to substitute the limit beta to alpha. So minus lambda divided by 4 pi epsilon d, the limit is sin alpha minus sin beta, right? So one more negative is available. While multiplying negative, what we got? Minus sin alpha plus sin beta, right? So finally we can exchange this value, lambda divided by 4 pi epsilon d sin beta minus sin alpha. This will be vertical component. Then the total component, I will get the total component. The resultant electric field intensity is nothing but E equal to square root of vertical component square plus horizontal component square plus vertical component square. E equal to square root of EH square plus EV square, right? So in this video we discuss the electric field intensity, the definition for electric field intensity, then charge distribution, 3 type of charge distribution, then electric field intensity due to a finite wire. We got the expression for horizontal component, vertical component, then finally we got the total component. Welcome viewers. In this video we will see the electric field intensity due to a charged disk. The charged disk is available. In that we are going to see what is the electric field intensity. A disk is with a radius a meter, that is uniformly charged with the charge density sigma coulomb per meter square. That is nothing but surface charge density. So a charged disk is nothing but like a CD, compact disk. The entire surface we are going to consider. So that here we are using the charge density sigma coulomb per meter square, right? By referring this diagram, this is the charged disk with radius a meter. We have the charged disk with radius a meter available. The disk is assumed to be having several rings of increasing radius. Starting from 0, there are n number of rings are available. Starting from 0, the radius of the rings keep on increases and reaches the maximum value of radius a. In this we consider one ring at a distance x meter. The ring is assumed to be having several rings of increasing radius. In that we consider one ring for the calculation purpose at a distance x meter. Our aim is to find the electric field intensity at this point P. The distance between this point P and the center of the disk is d meters. The distance between point P and this small segment is r meter. This will be x meter. So this triangle is drawn separately here, d x r. During the calculation we can refer this triangle. So this is a small segment dx. The angle will be alpha. So when the radius increases, the angle alpha will increase. The radius increases from 0 to a. So in terms of angle, it increases from 0 to alpha. During the limit, we need this value alpha, right? So we have the charged disk with radius a. It is assumed to be having several rings. We consider one ring at a distance x meter. The thickness is dx. Our aim is to find the electric field at this point P, which is at a distance d meter from the center of the ring. The distance between this point and point P is r meter. This will be x meter. So this triangle is drawn separately. Because of surface charge density, sigma equal to dq divided by ds. From that, dq equal to sigma into ds, right? So it is given in terms of surface charge density. So the description is given here. It is required to determine the electric field intensity at point P, which is at a distance d meter from the center of the disk, right? Our aim is to find the electric field intensity at this point P, which is at a distance d meter from the center of the disk. The disk is assumed to be formed by several rings of increasing radius from 0 to a. They keep on increasing. Several rings are available. In that, we consider one ring of radius x meter with a thickness of dx, right? So due to this small ring, the electric field intensity will be dE due to this small charge dq. The charge is small, so the electric field also small, dE. By integrating, we will get the total electric field intensity. So another important point is the perpendicular field is 0. If we consider any object, perpendicular field, that is vertical component, will be 0. Only the differential x component is available. X component means horizontal component. You know that vertical component, horizontal component, two terms available. Horizontal component equal to total component multiplied by cos of theta. Vertical component equal to total component multiplied by sin of theta. So here vertical component is 0, only we have horizontal component is available. Now we'll start with the electric field intensity. General formula Q divided by 4 pi epsilon r square. Electric field intensity E equal to Q divided by 4 pi epsilon r square. We consider only small charge, so that dE equal to dQ divided by 4 pi epsilon r square. Only the horizontal component available, so that it is multiplied by cos theta, right? So small electric field, small charge, and this will be horizontal component. So that is nothing but dE equal to this dQ can be replaced by surface charge density sigma into ds. Already this is available in the near the diagram, sigma dot ds divided by 4 pi epsilon r square into cos theta. So finally we have dE equal to sigma ds divided by 4 pi epsilon r square into cos theta. Now we'll see the expression for this ds. But this S is nothing but surface area of the disk. It's like a compact disk. S equal to pi r square. You know that area of the disk will be pi r square. So here we need ds, so differentiate on both the side. So that ds equal to differentiation of pi r square. So ds equal to pi. The differentiation of r square is 2r into dr. Right? So that it is 2 pi r dr. The ds value will be 2 pi r into dr. But in the diagram we consider the x. We consider one small ring at x meter. So that 2 pi x dx. Right? ds equal to 2 pi x dx. Now we can replace this ds with 2 pi x dx. So that value is substituted here. d equal to sigma, this ds is 2 pi x dx divided by 4 pi epsilon by epsilon r square into cos theta. This 2 pi, here the 2 pi got cancelled. So what we got, sigma x dx divided by 2 epsilon r square into cos theta. We'll take this is equation number 1. So after substituting all the value, we got this expression. Now we have one triangle is available. From the triangle, From this triangle we are going to find the expression for x followed by dx and r. Right, x followed by dx and r we can calculate, we can found from this triangle. So first we will find the tan theta. Tan theta is nothing but opposite side by adjacent side. So this is theta, opposite side is x, adjacent side is d. So x by d, right? So tan theta equal to x by d, right? So that x equal to tan theta into d. You cross multiply this, so that x equal to d tan theta. Now we got the expression for x equal to d tan theta. We need dx also, so that differentiate on both the side. So dx equal to differentiation of d tan theta. So dx equal to d, differentiation of tan theta is nothing but secant square theta into d theta. So dx will be d secant square theta d theta. Right. So we got the expression for x as well as dx. Now we can go with the cos theta. Cos theta equal to adjacent side by hypotenuse. Cos theta equal to adjacent side by hypotenuse. So d divided by r. We cross multiply this, right? You exchange these two values. So r equal to d by cos theta. So that r equal to 1 divided by cos theta is secant theta. So that r equal to d secant theta. Now we got the expression for r also. Now we are going to substitute this x value, dx value and r value, r expression in this equation number 1. Now we'll substitute this value x, dx and r in equation number 1. What is equation number 1? Sigma x dx divided by 2 epsilon r square into cos theta. That is the expression for, that is the equation 1. Now we'll substitute sigma x is nothing but d tan theta, dx is nothing but d secant square theta into d theta. Again this cos theta is available, divided by 2 epsilon r square. R square is d square secant square theta. Right, d value, dx value and r value is are substituted. The secant square got cancelled. Here d square is available, here also d available 2 times. So d square also got cancelled. So what we have, sigma tan theta cos theta d theta divided by 2 epsilon. After cancelling this we got this value. So this tan theta can be written as sin theta by cos theta. Sigma divided by 2 epsilon, tan theta is written as sin theta by cos theta into cos theta d theta. So this cos theta got cancelled. So what we got, dE equal to sigma divided by 2 epsilon sin theta d theta. Now we got, after substituting all the value, we got this expression. So this is due to small charge. So by integrating on both the side, we'll get the total electric field intensity. Right? Now we'll go for the integration. So integral dE equal to integral sigma divided by 2 epsilon sin theta d theta. What is the limit for this integration? We need to consider entire radius of the disk. Entire radius is a meter. But the difference, that the integration with respect to theta, so that we are considering the angle alpha. Right? So when the radius increases, the alpha also increases. So we are taking the limit 0 to alpha, very equivalent to 0 to a. Right? So sigma divided by 2 epsilon is constant. Only we have sin theta. Integral sin theta is minus cos theta. We need to substitute the limit 0 and alpha, upper and lower limit. So sigma divided by 2 epsilon, this while substituting the upper limit minus cos alpha plus. So already one minus is there. While substituting lower limit, we have one more minus. So it becomes plus cos theta, cos 0. So sigma divided by 2 epsilon minus cos alpha plus cos 0 value will be 1. Right? So while rewriting, the electric field intensity E equal to sigma divided by 2 epsilon 1 minus cos alpha. Right? So this is the final expression for electric field intensity due to a charged disk. Sigma divided by 2 epsilon 1 minus cos alpha. Now next we'll see the electric field intensity due to charged ring, right? We'll see that. Now followed by the disk, we'll see the charged ring, electric field intensity due to the charged ring. What is this charged ring? Yes, a wire of small cross section is bent in the form of circular ring. One lengthy wire is available, two ends are joined together and form the circular ring. So here the wire is available, so that we are using linear charge density, lambda equal to dq by dl, so that dq equal to lambda into dl. Because of linear, because of wire, lengthy wire is there, so that we are using linear charge density. The wire is uniformly charged with the charge density of lambda coulomb per meter. Right, here we are using the linear charge density, so that we are using lambda. Now we'll refer the diagram. So one lengthy wire is available. Now the lengthy wire is joined together. Two ends are joined together and form the charged ring. Right, the radius is a meter. So the length of the wire is nothing but circumference of this ring. Both are equal. Lengthy wire become the ring, so circumference of the ring is equal to length. So our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. Here we consider one small segment dl. L is the length, dl means small length. The distance between this segment and point P is r meter. This angle will be alpha. Right, similarly this angle also alpha. So this triangle is drawn separately here, A R H, with an angle alpha. From that, if you find cos alpha means adjacent side by hypotenuse, h by r. During the calculation we can use this cos alpha equal to h by r. So one lengthy wire is available. The two ends of the lengthy wire is joined together and form the circular ring. The radius is a. Our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. We consider one small segment dl. The distance between these two is r meter. This triangle is drawn separately with an angle alpha. Now we'll see the description. It is required to determine the electric field intensity at point P, which is at a distance h meter from the center of the ring. Right? We have the point P, which is located at a distance h meter. We consider only small charge, so that the electric field intensity also small, dE. Right? So dE is nothing but electric field intensity due to the point charge dq. So now we'll consider the small length dl. At the small length dl, the charge will be dq. Right? Now we'll go to the derivation. We know that electric field intensity E equal to Q divided by 4 pi epsilon r square. Due to small charge, it becomes dE equal to dq divided by 4 pi epsilon r square. Only horizontal component available, so that cos alpha. Right? So the dq can be replaced by lambda into dl, linear charge density. Right? So lambda dl divided by 4 pi epsilon r square into cos alpha. This lambda L is nothing but the circumference. I already told circumference, that is a into d theta, that is radius as well as theta. So when the circle it is rotates, the theta also varies, so it can be replaced by a d theta, this dl. So this is only the small electric field. By integrating on both the sides, we will get the total electric field. So integral dE equal to integral lambda a cos alpha d theta divided by 4 pi epsilon r square. What is the limit? 0 to 2 pi, that is 360 degree. This d theta vary from 0 to 360 degree rotation circle. Because of ring, it is 360 degree. Right? So in this, lambda a cos alpha divided by 4 pi epsilon r square is constant. Only we have d theta. right? So the integral d theta is theta. We have to substitute the limit 0 to 2 pi. So while substituting, what will happen? Lambda a cos alpha divided by 4 pi epsilon r square into 2 pi. Lower limit is 0, only 2 pi. This got cancelled. The 2 is there. So that lambda a cos alpha divided by 2 epsilon r square. Already we have the cos alpha value, that is h by r. Near the triangle it is available. So that lambda a h divided by 2 epsilon r cube. Finally we got the expression for electric field intensity due to the charged ring is E equal to lambda a h divided by 2 epsilon r cube. So in this video we got the expression for electric field intensity due to charged disk and charged ring. Welcome viewers. In this video we'll see the work done followed by potential and potential difference. First we'll see the work done. So work done is nothing but a charge is Q is kept at the electric field that will experience a force in the direction of electric field. If you place a charge in the electric field, what will happen? The force will be developed on the charge. We are referring this diagram. Here the charge is available. This plus minus is the electric field. This is nothing but a electric field. In that electric field, charge is placed. So due to this electric field on the charge, the force is created. Force is developed. That is called F. On opposite side, we are having applied force, Fa. Force is applied on the opposite side. Electric field is available. Charge is placed. Due to electric field, this charge experiences a force, that is nothing but F. On opposite side, we are applying one more force, Fa. If both are equal, then the charge will be remain in the same place. Suppose if Fa is greater than F, what will happen? The charge will move from this point A to point B. Right? If Fa applied force is greater than the force developed, mean the charge will move from the point A to point B. So what is the force applied and what is the distance moved is nothing but a work done. Right? Fa dot dl. So this description is given. F is the force experienced by the charge Q. Fa is the force applied on the opposite direction. If magnitude of Fa is equal to F, they remain same place, equilibrium. If Fa is slightly greater, then the charge will move from A to B. So the small work done by moving the charge is nothing but Fa dot dl. Very simple. So we are applying the force Fa. The charge is moving from one place to another place, that is called dl. So Fa dot dl is nothing but the work done by the charge. Fa dot dl. Right? So the total work done in moving a charge from A to B can be obtained by line integration. So this is due to only small length. The total work done can be obtained by the integrating on both the sides. We will get the total work done. So work done equal to integral A to B Fa dot dl. Right? A to B is the 2 points. In between A and B only the charge is moving. This is the applied force into dl. But F and F, this Fa is equal and opposite to the force developed. That is Fa equal to minus F. So that we can replace this Fa as minus F. Right? Now this is the applied force. Now it is replaced with the force developed. Fa and F are equal but in opposite, negative. So that minus Fa dot dl. But E equal to F by Q. Electric field intensity equal to force divided by charge. So cross multiply this. Force equal to electric field into charge. F equal to EQ. So that we can replace this F as E into Q dot dl. Right? Now the force is replaced with electric field intensity and charge from this relation. So finally what we got, work done equal to minus, you bring this q outside, it is a constant, minus q integral a to b E dot dl. So the general expression for the work done is nothing but minus q integral a to b E dot dl, right? Now we'll see the potential, electric potential. What is the definition for electric potential? Is also called as absolute potential. Is defined as the work done in moving a unit positive charge, right? Work done in moving a unit positive charge from infinite to the field point. Absolute means it is from infinite to the field point. We are going to move the charges, positive charge, from infinite point to the field point, right? So the work done in moving a unit positive charge from infinite to the field point. Now we'll first write the work done. What is work done? Just now we discussed minus q integral a to b E dot dl. Work done is nothing but minus q integral a to b E dot dl, right? Now bring this charge in the denominator. So that work done divided by charge equal to minus integral a to b E dot dl, right? Work done by charge, what is the work done by the charge? From the definition it is clearly given, work done in moving a unit positive charge. So work done by charge is nothing but potential V, right? So the potential V is nothing but work done by charge. So that is equal to minus integral a to b E dot dl, right? Work done by charge is potential, work done in moving a unit positive charge, so that this can be replaced as potential. Now we will replace this E as q divided by 4 pi epsilon x square into dx, right, with a limit of a to b. Q, it is a general formula, q divided by 4 pi epsilon x square into dx. Here we are having x, so here also dx. So this minus q divided by 4 pi epsilon is constant, only we have integral a to b 1 by x square into dx. These terms are constant. So minus q divided by 4 pi epsilon, integral 1 divided by x square is nothing but minus 1 by x, that you know that it is minus 1 by x. And what is the limit for this? It is nothing but work done in moving a unit charge from infinite to the field point. One is infinite, another one is the field point. So the limit is infinite, another point is r, right? It is clearly given in the definition, infinite to the field point. Now we'll substitute the limit, minus q divided by 4 pi epsilon. Here minus is there, minus 1 by r. Here 1 minus, in the lower limit 1 minus will be there, so it becomes plus 1 by infinite, so it becomes 0. Here 1 minus is available, here also 1 minus available, so q divided by 4 pi epsilon r. So the electric potential, the general formula is q divided by 4 pi epsilon r. Now we'll see the potential difference. What is potential difference? It is defined as the work done in moving a unit positive charge from point B to point A. Absolute potential means infinite to the point, field point, from infinite. But here potential difference is there. That means difference between 2 points, point B to point A. Same thing, work done in moving a unit positive charge, but it is from point B to point A. Right, it is clearly given. So potential difference VAB, right? VAB refers means the potential difference between A and B equal to integral a to b E dot dl. Normally B to A, one negative will be there, that is replaced by exchanging the limit a to b E dot dl, right? So directly we have got this expression. Now replace this E as q divided by 4 pi epsilon r square into dr. Here we are having r, so that it is given as dr, right? Now this q divided by 4 pi epsilon is constant, only we have integral a to b 1 by r square into dr. right? Other terms are constant. So q divided by 4 pi epsilon, the integral 1 by r square is minus 1 by r. Now what is the limit RA to RB? Because point A to point B, that is clearly given. So that we are taking RA, RB. Now substitute the limit q divided by 4 pi epsilon minus 1 by RB plus 1 by RA, right? So minus is there. While substituting the lower limit, it become plus. So we will rewrite this. So then q divided by 4 pi epsilon into 1 divided by RA minus 1 divided by RB. That is the potential difference between the 2 points A and B. The points are represented as RA, RB. Welcome viewers. In this video, we'll see the potential due to charged disk and charged ring. First, we'll see the potential due to the charged disk. Now we have a disk of radius A meter is available, that is uniformly charged with a surface charge density of sigma coulomb per meter square. So this charged disk is nothing but like a compact disk CD. Entire surface the charges are available, so we are using this surface charge density sigma coulomb per meter square. Now we'll refer this diagram. So we have the disk is available with radius A meters. The disk is assumed to be having several rings of increasing radius. For example, starting from 0, there are small rings are available. Keep on increases. The radius of the ring keep on increases up to going up to radius of the disk. So in this we consider one ring with a radius with a distance d meter. Right, the disk with radius is A. We are assuming that the ring is formed with several rings of increasing radius. In this we consider one ring at a distance x meter. The thickness is dx. Our aim is to find the potential at this point P, which is at a height of h meter from the center of the disk. Our aim is to find this potential at this point P, which is located at a height of h meter from the center of the ring. The distance between the small segment and point P is r meters. So this triangle is drawn separately. It will be used during the calculation. H, X and R. This triangle is drawn separately. This is a perpendicular. Here we are using the surface charge density, so sigma equal to dq divided by ds. We are assuming entire surface of the disk. So dq by ds, from that dq equal to sigma into ds. The dq can be represented as sigma into ds, right? So that description is given. The disk is assumed to be having several rings of increasing radius. That is from 0 to A, there are so many rings are available. In that we consider one ring at x meter with a thickness of dx. So our aim is to find the potential at this point P, which is at a distance h meter, right? Now we'll take this dV is the potential at this point P. The V is the total potential, dV is the potential due to small ring dx. So that the V become dV, right? Now the potential is given by V equal to Q divided by 4 pi epsilon R. The general formula for potential is V equal to Q divided by 4 pi epsilon R. Now we consider only small charge, so that V become dV. dV equal to dq divided by 4 pi epsilon R. But dq is nothing but sigma into ds, surface charge density. So dV equal to sigma ds divided by 4 pi epsilon R. After substituting all the value, we got this expression. Now we'll see the surface area. surface area is pi r square. Now we are having x, so that it is pi x square, surface area of the ring or disk. Differentiate on both the side, so ds equal to pi, the differentiation of x square is 2x dx. So it can be written as 2 pi x dx. ds is nothing but 2 pi x dx. Now this ds is substituted in the previous equation. dv equal to sigma 2 pi x dx divided by 4 pi epsilon r. So this 2 pi and 4 pi got cancelled, the 2 is there. So sigma x dx divided by 2 epsilon r. Right. So after substituting the surface area, we got this value. Now we'll go for the further simplification. Sigma x dx divided by 2 pi epsilon r. The r square from the triangle, based on the Pythagoras theorem, we can write r square equal to x square plus h square. That is r equal to square root of x square plus h square. So we can replace this r with this value, so that we got dv equal to sigma x dx divided by 2 epsilon square root of x square plus h square. But this is the due to only small charge and small potential. Then the total potential, I will get the total potential. The total potential due to the entire disk can be obtained by integration with a limit 0 to a. What is 0 to a? That is radius of the disk. We assume that there are n number of increasing radius rings are available. That rings are increasing from 0 to maximum radius of a. So the limit is from 0 to a. Right. So that integral, by integrating on both the side, dv, integral dv equal to integral 0 to a sigma x dx divided by 2 epsilon square root of x square plus h square. Integral dv is v. So 0 to a, this value. You take, this is equation number 1. Now the integration with respect to dx, the x is available both in numerator as well as denominator. Right? The x is available in numerator as well as denominator. We can use u by v method. But on alternate, we have substitution method is available. We can substitute this value so that it will be easier. You can do by u by v method also. Now we will go with substitution method, that is somewhat easier compared with u by v method. So in this substitution method, we are going to substitute x square plus h square equal to t square. That is, we are substituting x as a t. We are changing the value from x from t. Right? So x square plus h square equal to t square. So differentiate on both sides, so that 2x dx equal to 2t dt. This h is constant, so that only we have 2x dx 2t dt. The 2 got cancelled, so x dx equal to t dt. So x ds can be substituted with t dt, so that x value will be substituted as t value. Right. So from this, the t can be written as, the t square is this value, so t equal to square root of x square plus h square. Now we have two limits available, x equal to 0 and x equal to a. That also transfer into t terms, because now we transfer the x into t, so that this limit also should be changed into t term. Now substitute x equal to 0 in this expression. So t equal to square root of 0 plus h square, that is nothing but square root of h square is h, t equal to h. So for x equal to 0, the corresponding lower limit is t equal to h. Right? Now the limit also transfer into t term. Similarly, upper limit x equal to 0, substitute the 0, x equal to a, substitute here x equal to a, so that t equal to square root of a square plus h square. Now the upper limit also transfer into t term. Right? So this is the lower limit corresponding to t, this is the upper limit corresponding to t. This will be the substitution. X dx can be replaced by t dt. Now we'll replace this value, lower limit and upper limit, in the equation 1. right? All these values are substituted in equation 1, right? So 0 to a sigma x dx divided by 2 epsilon square root of x square plus h square is the equation 1. Now we'll replace this 0 as a h, because lower limit 0, the equivalent limit will be h. For upper limit a, the equivalent will be a square plus h square. Sigma, this x dx is nothing but t dt. We got that previously. So the x dx is t dt divided by 2 epsilon. What is this? Square root of x square plus h square, that is nothing but t. Right? So now it is simplified. This t got cancelled. So this sigma by 2 epsilon is constant. So integral lower limit is h, upper limit is square root of a square plus h square into dt. Now see this, the integration become very simpler. Because of substitution method, it is simplified. So integral dt is nothing but t. So integral dt is nothing but t. I can substitute the limit. So sigma divided by 2 epsilon, the upper limit, a square root of a square plus h square minus lower limit h. So this is the final expression for potential due to the charged disk, right? Whereby by using the substitution method, it is easily we got the final expression. Now we'll see the potential due to charged ring. Previously a disk is completed, now we'll go to the charged ring. How the ring is formed? A thin wire is bent in the form of circular ring. One thin wire is available, two ends are joined together and form the circular ring, right? So the length of the wire is nothing but circumference of the ring, right? Lengthy wire is brought into two ends are contact together and form the circular ring. Due to the lengthy wire, we are using linear charge density, lambda equal to dq by dl. From that, we cross multiply this, dq equal to lambda into dl. Because of lengthy wire, what we are having? Linear charge density lambda, referring the length of the wire. Now we'll see the diagram. So this is nothing but the ring. So the lengthy wire is there, the two ends are joined together and form the ring. The radius is a meters. What is our aim? I need to find the potential at this point P, which is at a height of h meter from the center of the ring. Our aim is to find the potential at this point P. Now consider one small segment dl. L is the total length, dl means small segment. The distance between the small segment and point P is r meters, right? This angle will be theta, d theta. Theta is the angle, d theta is the small angle, right? So we have the ring is available with the radius a. We are going to find the potential at this point P, which is at a height of h meter. We are consider one small segment. The distance between small segment and point P is r meter, right? So that description is given here. It is uniformly charged with a charge density lambda coulomb per meter. Because of lengthy wire, it is lambda coulomb per meter. What is our aim? To find the potential at point P, which is height of h meter from the center of the ring. The ring is assumed to be having several point charges. Because of lengthy wire, normally we have point charges. Now we'll consider this dV. V is the potential, dV means small potential due to the small segment dl, right? Now we'll go to the derivation. We know that V equal to Q divided by 4 pi epsilon r. General formula for potential is Q divided by 4 pi epsilon r. So due to small charge dq, the V become dV. So dV equal to dq divided by 4 pi epsilon r. Right. Now the dq can be replaced by lambda into dl. So dV equal to lambda dl divided by 4 pi epsilon r. So this is due to small length, this is due to small potential. So by integrating on both the side, we will get the total potential. So integral dV equal to integral lambda into dl divided by 4 pi epsilon r, right? So we will see this side. So integral dv is nothing but v. The lambda divided by 4 pi epsilon r is constant. Only we have integral dl. What is integral dl? Integral dl is nothing but L, length. What is the length? Length is nothing but circumference of the ring, because lengthy wire is bent in the form of ring. So the circumference of the ring is nothing but the length of the wire. So that is given here, 2 pi a. So integral dl is L. L is nothing but circumference, that is nothing but 2 pi a. So that v equal to lambda divided by 4 pi epsilon r. This dl is replaced as 2 pi a. So the 4 pi is there, here 2 pi is there, got cancelled. So lambda a divided by 2 epsilon r. So the final value will be, after cancelling this, what we got, v equal to lambda a divided by 2 epsilon r. This is the final expression for potential due to the charged ring, right? So in this video we saw the potential due to charged disk as well as charged ring. Welcome viewers. In this video we'll see the displacement density followed by the Gauss law. First we'll see the displacement density. This displacement density denoted by d. So that is nothing but q divided by 4 pi r square. What is that? This is a displacement per unit area. The definition of displacement density is displacement per unit area, q divided by 4 pi r square, right? It is a vector quantity. So that is given. It is a vector quantity, q divided by 4 pi r square. Now we'll see the relation between E and D, electric field intensity and displacement density. You know that electric field intensity is q divided by 4 pi epsilon r square. The general formula for electric field intensity, q divided by 4 pi epsilon r square. I will rewrite this, E equal to q divided by 4 pi r square into 1 by epsilon. The epsilon is written separately and q divided by 4 pi r square is written separately. So we know that q divided by 4 pi r square, this is nothing but displacement density. So we can replace this by d. So that is nothing but E equal to d divided by epsilon, right? D divided by epsilon. We cross multiply this so that epsilon E equal to d, that can be written as d equal to epsilon E. The relation between d and E is given as d equal to epsilon into E. Now we'll see the Gauss law. The Gauss law is flux coming out of a charged body is equal to amount of charge enclosed, pi equal to q. That is a statement given by the Gauss law. If any charged body is there, the flux will coming out. That flux is equal to the what is the amount of charge enclosed in the body. So that is a statement given, pi equal to q. Very simple. Charged body is there, from that flux is produced. So that flux is equal to amount of charge enclosed, right? Both are equal, pi equal to q. Now we'll go to the proof of this Gauss law. Let us consider one charge is placed at the origin, q. We have one small segment, small area, small differential area, ds at a distance r meter. The d is the displacement density along with this small segment, right? See the angle between these two are normal. Both are in same line. The angle between these two is 0. The small segment ds and displacement density both are at an angle of 0 degree, right? So we have charge q is placed at the origin. One small segment area is available at a distance r meter. Along with that we have displacement density vector. Now we'll see this. What is displacement density? D. D equal to d pi by ds, flux per unit area. So this d pi is small flux, so that the small area ds, d pi by ds. We are consider the small area, so the flux coming out of the small area also d pi, right? So we cross multiply this so that d pi equal to d dot ds. So this d dot ds, that is nothing but a vector dot b vector. What is a vector dot b vector? That is ab cos theta. A vector dot b vector equal to ab cos theta. So we can write d dot ds into cos theta. What is the angle between d and ds? In the diagram it is clear. The angle between d and ds is 0 degree. Both are available in the same direction, 0 degree. So cos 0 will be 1. So we can write d pi equal to d dot ds, d into ds, right? So this d pi flux is the small flux due to the small area. So by integrating on both the side, we'll get the total flux. So integral d pi equal to integral d dot ds. Integral d pi is nothing but pi, that is equal to integral d dot ds, right? So pi equal to integral d dot ds. We can replace this displacement density as q divided by 4 pi r square, because displacement density vector is q divided by 4 pi r square. So this is constant, so we can take it as outside. Only we have integral ds. What is integral ds? Integral ds is s. S is nothing but surface area. Right. What is the area, surface area? If any charge, we assume that it is spherical. So it is pi r square. For simplification purpose, we consider 4 pi r square. So this 4 pi r square got cancelled. Finally, what we got? Pi equal to q. The flux coming out of a charged body is equal to amount of charge enclosed. So after simplification, we got that the flux is equal to charge. Now we'll see the applications of Gauss law. What is the main application of Gauss law? Gauss law can be used to solve complex electrostatic problem involving unique symmetrics, such as, right? Complex problem can be solved, that is the electric field intensity due to uniformly charged infinite state wire. Uniformly charged, any object uniformly charged, in that we can find the what is the electric field intensity, either due to infinite state wire or infinite plate sheet or spherical cell, right? We can able to find the variation of the electric field intensity of various objects, such as infinite state wire, infinite plate sheet and spherical cell. So the main application of Gauss law is finding the variation of electric field inside as well as outside of the object, either straight wire or plate or shell. So based on that, we'll see two problems. One is based on the spherical cell, another one spherical cell with the entire volume. So the application is to find the electric field intensity. So in this problem 1, determine the variation of electric field intensity from point to point for a single spherical cell of charge with radius r1, right? We are going to find the what is the variation of the electric field intensity for a spherical cell with the charge is available with the radius is r1. We need to find what is the electric field intensity inside as well as outside of this spherical cell. The radius is r1, right? We'll see the diagram. So we consider that spherical cell has charge only on its surface, not inside. Inside the charges are not available, only on the surface the charges are available, right? We'll see this diagram. So this is a spherical cell with radius r1. Our aim is to find the variation between E and R. So this R is nothing but imaginary spherical, imaginary sphere, Gaussian spherical surface. We consider Gaussian spherical surface with radius R. So this, when the R increases, small r increases, what will happen to the electric field intensity? That we are going to analyze, right? R1 is the radius of the spherical cell. The small r is the imaginary spherical surface. Outside we consider that radius is small r. So if the small r, the radius increases, what will happen to the electric field intensity? That we are going to analyze, right? So this is the first condition, where first we consider r is less than r1. r is less than r1. That is, imaginary radius is less than r1. That is, what is the meaning? The imaginary surface available inside the spherical cell, right? If r is less than r1 means, if r is less than r1, this r is less than r1 means the imaginary, the Gaussian cylindrical surface, spherical surface available inside, right? This r is available inside, right? So we know that E equal to Q divided by 4 pi epsilon r square. But inside the spherical cell, the charges are not available. Only on the surface, the charges are available. So the inside the spherical cell, the charge is 0, Q is 0, so that E is also 0, right? The case 1, what we consider, R is less than R1, that is, the Gaussian spherical surface available inside the sphere. The formula is Q divided by 4 pi epsilon r square. In this, inside the spherical, the charges are not available. Only on the surface, the charges are available. So the charge is 0. So the electric field intensity also 0 inside the spherical cell. So that is written here. So this is inside. Inside of the spherical cell, the charge is, the electric field intensity is not available, 0. Right? This is the first case. R is less than R1. Right. Now we'll go to the second condition. R greater than R1. What is the meaning? This R greater than R1 means this R is available outside the spherical cell. R is greater than R1. What is available in the diagram as it is? This R is located outside. So what will happen? We'll see that if it is located outside, E equal to Q divided by 4 pi epsilon r square. Now the charge is available. Outside the charge is available. In the previous case, inside the charge is not available. Now the charge is available. Now see the relation between E and R. E is directly proportional to 1 by r square. Right? Inversely proportional is there. When R increases, E will decrease. Right? When the radius increases, the E will decrease, right? So that is clearly given in the diagram. So this is the surface. On the surface, the electric field intensity is maximum. Thereafter, when the radius increases, it is keep on decreases. The electric field intensity will keep on decreases. Because on the surface, the charges are available. So on the surface, the electric field intensity is maximum. Thereafter, when the radius increases, electricity field will be decreases. Similarly, this side also. So from this diagram, it is clear. Inside, there is electric field intensity is 0. On the surface, it is maximum. Thereafter, when distance increases, electricity field will be decreases on both the sides. So we can easily identify what is the variation of electric field intensity. What is available inside, on the surface, and out of the surface. Inside the surface 0, on the surface maximum, thereafter decreases on both the sides. Now we'll go to the second problem. In this, the volume in spherical coordinate is described. Volume, that means the entire volume where the charges are available inside as well as on the surface. In previous problem, the charges are available only on the surface, but here we consider volume, right? Contains the rho coulomb per meter cube. So entire volume, the charge is available. This is the charge density, rho coulomb per meter cube. So by using Gauss law, we need to determine what is the variation of electric field intensity in the spherical charged body. Right? So the previous problem, charges available only on the surface, but in this, the charges available in the entire volume, inside as well as on the surface. Now we'll see the diagram. Here the radius is A. Previously it is R1, capital R1, now it is A. Radius of the spherical cell is A. This is the imaginary radius. We consider one Gaussian spherical surface with the radius small r. Our aim is to find the variation between this electric field intensity and radius r. When the radius r, imaginary radius increases, what will happen to the electric field intensity? Right? So before that, we'll see what is rho. Volume charge density is nothing but Q divided by V, cross multiply this, Q equal to rho into V. Charge equal to volume charge density multiplied by volume, right? So Q can be represented as rho into V based on this formula. Now we'll have two different cases. This R is less than A. R is less than A means the imaginary Gaussian spherical surface available inside, right? So we'll see this. R is less than A. R is less than A means this R is available in the inside of the spherical cell. Now we'll apply the Gauss law. E equal to Q divided by 4 pi epsilon R square. Now Q can be replaced as rho V. We already discussed rho V. So rho divided by 4 pi epsilon R square. What is V? V, volume of the sphere, is nothing but 4 by 3 pi R cube. 4 by 3 pi R cube. What is the value of R here? R is nothing but less than A. Suppose the A is 10 centimeter mean R will be less than 10 centimeter. It may be 9 centimeter or 8 centimeter or 1 centimeter. Right? So R value is a known value here because R is less than A. A value is the defined value. A is the radius of the spherical cell. The radius may be 10 centimeter or 20 centimeter. If it is 10 or 20 centimeter mean R is less than 10 or 20 centimeter. So the value of R is known value. From A we can easily identify the value of R. So 4 by 3 pi R cube. Now this 4 pi got cancelled. Here R square is there, here R cube is there. So R square got cancelled. So finally what we have? E equal to rho R divided by 3 epsilon. Right? Rho into R divided by 3 into epsilon. Now see the relation between E and R. E is directly proportional to R. When radius increases, E also will increase. E will also increase. What is this here? R? R is the imaginary radius that is now available inside. So when R increases, E also increases. Now we'll see the diagram. See this. When the R increases, electricity field also increases. At the center it is 0. Thereafter, when the R increases, the electricity field increases and reaches the maximum value at the surface, on the surface. Similarly, this side also. So in the previous problem, inside the electric field intensity is 0, but here electric field intensity increases linearly in the inside of the spherical cell because the charge is available in the entire volume of the sphere as a volume charge density, so that the electric field intensity increases, reaches maximum value at this surface. Now we'll go to the second condition, R greater than A. What is R greater than A mean? Similar to this diagram, R is available outside. What the diagram drawn is applicable for second case. R is greater than A. The spherical cell is available, imaginary spherical cell available outside the sphere. Right. Now we'll see the relation. E equal to Q divided by 4 pi epsilon R square. This Q is replaced by rho V. Right. So that can be written as rho divided by 4 pi epsilon R square into V. What is the V here? 4 by 3 pi A cube, not R cube. Previously we have R cube. Why we are using A? Because R is greater than A. Suppose A equal to 10 centimeter means R will be greater than 10 centimeter. It may be 11 centimeter or 100 centimeter or 1000 centimeter. It will go up to infinite. So we cannot use this value R. Only the defined value A can be used here. Because A is the known value, R is it will go up to infinite. Greater than A means it will go up to infinite. But in this case, R less than A means if A is 10 centimeter, R will be automatically less than 10 centimeter. It may be 1 centimeter or 2 centimeter up to 9 centimeter. It's a known value. From A, we can easily identify the value of R. But here greater than R, so R is greater means we cannot that. It will go up to infinite. So we can use only the known value A. A is the known value. So that we are using 4 by 3 pi A cube. Here we are using 4 by 3 pi R cube. Because here A is the known value, but here R is the known value from A, but here R is maybe go up to infinite, so we are using A, right? So due to that, what will happen? Only this 4 pi got cancelled. So pi A cube divided by 3 epsilon R square. What we got? This R square got not got cancelled. Rho A cube divided by 3 epsilon R square. See the relation between E and R. E is directly proportional to 1 divided by R square, right? Inversely proportional to R square. When the radius increases, E will decreases in a square manner. E is directly proportional to 1 by R square. See this, that will be reflected in the diagram. So here it is maximum. So when the R increases, the electric field intensity will decreases, not a linear manner, in a parabolic manner, because E is directly proportional to 1 by R square. It keep on decreases on both the side, right? So in this problem, when the spherical cell, the imaginary spherical cell is inside, if you consider, the electric field intensity increases in a linear manner because charges are available inside. Reaches maximum on the surface, thereafter decreases because E is directly proportional to 1 by R square here, right? So we can easily identify the variation of the electric field intensity in the spherical cell with volume charge density. Inside increases linearly, outside decreases in a parabolic manner. Welcome viewers. In this video, we'll see the relation between electric potential and electric field intensity. Electric potential V and electric field intensity E, followed by some problems. First, we'll see the relation between E and V, electric field intensity and potential V. Let us consider this diagram. So the point charge is placed at the origin. So charge Q is placed at the origin. The point P is located at a distance R meter. Here one point P is located at a distance R meter. This is the unit vector. AR is the unit vector. So this is the electric field intensity. Due to the charge at point P, the electric field intensity is created, right? So the charge is placed at the origin. Point P is located at a distance R meter. AR is the unit vector. E is the electric field intensity at point P due to the charge Q. I will see the formula for this. So E equal to Q divided by 4 pi epsilon R square into AR cap. Electric field intensity is a general formula. Q divided by 4 pi epsilon R square. But we know that the del of 1 by R equal to minus 1 by R square into AR. The del operator. What is the del operator? It is a partial differentiation. Dou by dou x, dou by dou y, or dou by dou z. In case of R, it is dou by dou r, dou by dou pi, dou by dou theta, like that. Here only R is there. So by differentiating 1 by R is nothing but minus 1 by R square. So in this 1 by R square available here can be replaced by del of 1 by R. Okay. So from this relation, what we got? Del 1 by R equal to minus 1 by R square. See this in this expression E, Q divided by 4 pi epsilon R square. So 1 by R square. This 1 by R square is replaced by this value, del of 1 by R with negative. So that is given here. Q divided by 4 pi epsilon, right? 1 divided by this 1 by R square, now replaced by del of 1 by R. So by simplifying, we can write minus del Q divided by 4 pi epsilon R. What is Q divided by 4 pi epsilon R? That is nothing but potential V, right? So now we can replace this as a V, so that E equal to minus del V. So finally what we got? Electric field intensity equal to minus del V. What is the meaning for this? The electric field is a negative potential gradient. Electric field and potential are negative gradient. This equation indicates the direction of electric field is opposite to the direction of rise of potential, right? Both are negative gradient. The rise in electric field intensity is opposite to the rise of potential. E equal to minus del V. So by using this relation, we'll see a few problems. We'll see the first problem. The first problem is determine the electric field intensity. We need to find the electric field intensity E and unit vector for the point at a point 1, 1, minus 1. In the field of potential is given by V equal to 2x square y cube Z. So in this problem, we need to find electric field intensity and unit vector. The potential is given. The potential equation is given 2x square y cube Z, and point also given 1, 1, minus 1. So from V, we need to find the E value, expression for E. So we know that the relation is available, E equal to minus del V. So by using this relation, we can find the electric field intensity from potential. What is del V? The V is nothing but 2x square y cube Z. The value of V is given in the problem. What is del operator? I already told, is a partial differentiation. Dou by dou x into Ax vector, dou by dou y into Ay vector, plus dou by dou Z Az vector. Partial differentiation with x, y and Z. Now multiply this value, dou by dou x of 2x square y cube Z into Ax vector, dou by dou y of 2x square y cube Z into Ay vector, and dou by dou Z of 2x square y cube Z into Az vector. So what is the meaning? This one we need to differentiate with respect to x. That is, remaining terms are constant. Y and Z are constant. What is the meaning of dou by dou y? We have to differentiate with respect to y. X and Z is constant. Dou by dou Z means we need to differentiate with respect to Z. X and y are constant. Right? So while differentiating, what we are getting? Dou by dou x. So the x square. Differentiation of x square is 2x. Already one 2 is there, so that it is 4x y cube Z. Right? This y cube Z is written as it is. X square is, the differentiation of x square is 2x. Already one 2 is there, so it becomes 4x. Then this one differentiation with respect to y. Right? So differentiation with respect to y cube. Differentiation of y cube is 3y square. Differentiation of y cube is 3y square. 3, already here 2 is there. 2 into 3, 6. 6x square y square Z into Ay vector. Right. Then differentiation with respect to Z. Here Z is available. So differentiation of Z is 1. So only we have 2x square y cube into Az vector. Right. So here we are differentiated with respect to x. That is 2x means x square means 2x. Y cube means 3y square. Z means 1. Now we got the relation. Now we got the expression for E. Now the point is given 1, 1, minus 1. So that we can substitute this point, so that we'll get the unit vector. E at 1, 1, minus 1. That is, we need to substitute x as 1, y equal to 1 and z equal to minus 1. Right? So 4 into x is 1. Then y cube, 1 cube. Z is minus 1 into Ax. Similarly, 6 x square is 1. Y square 1. Z minus 1. Into 2 into x square y cube. Here Z is not available. Right? Only here and here Z is available. Here Z is not available. So that due to negative, what we are getting, already one negative available outside, minus 4x minus 6ay. Here there is no negative, so it is plus 2az. Right? So minus of minus 4ax minus 6ay plus 2az. Now multiply this negative inside, so these two become positive. 4ax vector plus 6ay vector minus 2az vector. Because of positive, it becomes negative. What is unit vector? Unit vector is nothing but vector by scalar. The formula for unit vector is r vector by r, modulus of r. So the r vector is 4ax vector plus 6ay vector minus 2az vector. What is the magnitude square root of this? All these terms should be squared. 4 square plus 6 square plus minus 2 square. So that is equal to 56. So the unit vector will be 4ax vector plus 6ay vector minus 2az vector divided by square root of 56. So this is a unit vector. So this is nothing but electric field intensity. We calculated from the potential. This is the first answer, electric field intensity. After substituting the point, we got unit vector, this value. So in the second problem, we'll see that two identical spherical charges are available. Conducting sphere having a charges of 2 into 10 to the power minus 9 coulomb and minus 0.5 into 10 to the power minus 9 coulomb. Two charges in a spherical form is available. One value is 2 into 10 to the power minus 9 coulomb. Another is 0.5 into 10 to the power minus 9 coulomb. It is placed at a distance 4 centimeter. We need to find what is the force between them if they are brought into contact and separated by 4 centimeter. Right? Both are brought into contact, mixed together. Again it is separated by 4 centimeter. In both the cases we need to find what is the force between them. Before brought into contact, after brought into contact, what is the force between them? That is the question. Right? So this is a Q1 value, this is a Q2 value. The distance between is 4 centimeter. Right? So the given data, this is Q1, Q2 and R value. So before brought into contact, first we will find the value. The two charges before brought into contact. So we can take this value as it is. Q1 is 2 into 10 to the power minus 7. Q2 is 0.5 minus 0.5 into 10 to the power minus 7. Right? The formula is 9 into 10 to the power 9. It's a scalar, not a vector. 9 into 10 to the power 9 Q1 Q2 divided by R square. So 9 into 10 to the power 9 is Q1 value. 2 into 10 to the power minus 9 Q2 value minus 0.5 into 10 to the power minus 9 divided by 4 centimeter. So that it is 4 into 10 to the power minus 2, converting into meter. So what we got? Minus 5.625 into 10 to the power minus 6 Newton. So before brought into contact, as a normal condition, these two charges as it is, by using this value we calculated the forces minus 5.625 into 10 to the power minus 6 Newton. Right. Now the charges are brought into contact. Both are added together. Q equal to Q1 plus Q2. We added both the charges. So 2 into 10 to the power minus 9 minus 0.5 into 10 to the power minus 9. So what is the value? 2 here, that minus 0.5 there. So it is 1.5 into 10 to the power minus 9 coulomb. So while adding both the charges, what we got? 1.9 into 10 to the power minus 9 coulomb. Now again it is separated, brought into contact. Again it is separated into two parts. That also placed at 4 centimeter. What will happen if it is separated? The charges will be splitted into two equal parts. That is the important thing. This is the one value 2. Another charge is minus 0.5. Both are added together. What we got? 1.5. But while splitting, the nature of the charge is it will split into two equal parts. Right? That is the one nature, one property of the charge. Charge will be splitted into two equal parts. So that Q1 and Q2 equal to half of this value. 1.5 is 1.5 into 10 to the power minus 2 divided by 2 means 0.75 into 10 to the power minus 9 coulomb. It is splitted into exactly half. 0.75 minus 9 into 10 to the power minus 9 coulomb. Now both Q1 Q2 are same value. So by using this value we can find the force again. Right? The same formula, 9 into 10 to the power 9, this is Q1 and Q2, both are equal, divided by the distance. So what we got? 3.164 into 10 to the power minus 6 Newton. Right? So the first condition what we calculated without normal case, without brought into contact. After brought into contact, both are mixed together. The important point is while splitting, it will split into two equal parts. Exactly half of the charge will be splitted, right? So the 1.5 means the while splitting into 2, it will be 0.75 into 10 to the power minus 9 coulomb. Both Q1 and Q2 will be same value, splitted into equal parts, right? By using this charge, we calculated the forces 3.164 into 10 to the power minus 6 Newton. Now we'll see the third problem. Three equal positive charges. The value is 4 into 10 to the power minus 9. Each are located at three corners of the square of side 20 centimeter. Right, the one square is available with the side 20 centimeter. At the three corners, this 4 into 10 to the power minus 9 coulomb charge is placed. All three corners are equal value. Now our question is determine the magnitude and direction of electric field at the back end corner of the square. The three corners, the charges are placed. One more corner is there. At that corner, we need to find what is the electric field intensity, magnitude as well as direction. So this is the given problem. We will see the diagram. So this is a square with 20 centimeter, right? R equal to 20 centimeter, that is 20 into 10 to the power minus 2, that is 0.2 meter, right? It's a square with 0.2 meter, so 0.2 is given. These three corners, the charges are placed. We will assume that Q1, Q2, Q3. These three corners, the charges are placed. What is the value of the charge? 4 into 10 to the power minus 9 coulomb. The charge value is equal. All three corners having equal amount of charge. Our aim is the remaining corner is available. We need to find, the question is, we need to find the electric field intensity at the fourth corner due to this Q1, Q2 and Q3, right? So that is nothing but we will take it as this E2. We will see one by one. So at this corner, we need to find the electric field intensity. First consider Q1. So the electric field intensity due to Q1 will be E1 in this direction. Both are available in the same line. So only one component E1, right? So the E1 is the electric field intensity on point P due to the charge Q1. Due to both are placed in the same line, only we have the E1, only horizontal component. Now consider Q3. Q3, due to Q3, the electric field intensity available in point P is E3. These two also available in the same line, so we have only one component. E3 is a vertical component, right? So E1 is the electric field intensity due to Q1. E3 is the electric field intensity at point P due to Q3. So these are all available in the same line. But we'll consider in Q2, this corner, the electric field intensity is E2 at this point P, but it is available at an angle of 45 degree. It is located at an angle of 45 degree. But Q1 and Q2 placed at the same line. There is no horizontal or vertical component. But if these two are, this point and this point is placed at a distance at an angle of 45 degree. So that this E2 is splitted into two components, vertical component and horizontal component, EV, EH. The sum of EV and EH equal to E2, right? So now what are the components we have? E1 is available, E3 is available, EV is available, EH is available. This E1 and EH, these two are horizontal component. E3 and EV, these two are vertical components. Like that we can find, easily we can able to find. So we will find E1, E3, EV and EH. So by adding all, we'll get the total electric field intensity at point P due to Q1, Q2 and Q3. Right? So first we'll consider the charge Q1. It is very simple. E equal to Q divided by 4 pi epsilon R square. That is the formula. This is a unit vector. right? Because the q1 located in the same line, so there is no other component, only we have E1 only. So E1 equal to Q divided by 4 pi epsilon R square. Q is 4 into 10 to the power minus 9 divided by 4 into pi into epsilon naught is 8.854 into 10 to the power minus 12. It is, we consider as a air medium. So the epsilon R equal to 1. And R value is 0.2. This 0.2 is available. 0.2 square. So what we got, E1 equal to 900 AX, voltage per meter, right? 900. So while considering Q1, the U1 value will be 900, only one component. Now consider Q2. While considering Q2, what is the thing? We have horizontal component as well as vertical component. Horizontal component is in general total component multiplied by cos of theta. Vertical component equal to total component multiplied by sin of theta. Here theta is 45 degree. It's a general formula. Horizontal component equal to total component multiplied by cos 45. Vertical component equal to total component multiplied by sin 45. Now what is this R value? We need this R value. That is the important thing. From the diagram, see this, the distance between point P and Q1 is 0.2. Distance between point P and Q3 also 0.2. But distance between Q2 and point P is not known. We need to find from Pythagoras theorem, because these two values are known, 0.2, 0.2. So according to Pythagoras theorem, this value, let us consider R equal to square root of R square equal to 0.2 square plus 0.2 square. So we need this distance. This distance can be calculated using this Pythagoras theorem, right? R equal to square root of 0.2 square plus 0.2 square. So finally what we got? Square root of 0.08, that is nothing but 0.2828 meter, right? So what we need is, this distance is needed, that is 0.2828 meter. That is calculated from the Pythagoras theorem, right? Now we need to find what is the horizontal component and vertical component. Now we got the value of R. So while considering the second charge, E2 is the vector sum of horizontal component plus vertical component. Horizontal component is E2 cos 45 into AX vector plus E2 sin 45 into AY vector. This is the horizontal component, this will be vertical component. You take the E2 outside, so we have cos 45 AX plus sin 45 AY. What is E? Q divided by 4 pi epsilon R square. So this R is already we calculated based on the Pythagoras theorem, into cos 45 AX plus sin 45 AY. Right. Now we'll substitute the value. The Q is 4 into 10 to the power minus 9. This cos 45 is 1 by root 2 into AX. Sin 45 also 1 by root 2 into AY. Now A in 4 into pi into epsilon is epsilon naught, 8.854 into 10 to the power minus 12 into R. R value we calculated 0.2828 square, right? So by simplifying this, what we got? 450. By multiplying inside, what we got? 320 AX plus 320 AY, right? So while considering the second charge, we have horizontal and vertical component. So that is given as 320 AX plus 320 AY, right? Now we'll go to the third charge. Third charge, again it is same, because there is the charge value and distance is already equal. So the E3 is equal to E1. E1 we already calculated 900 AX. So E3 also 900 AY. Only it is available as a vertical. So that no need to calculate again. The already calculated E1 value taken as E3. Both E1 and E3 are same. Only E1 is the horizontal component, E3 will be vertical component. Now we got all three values due to Q1, Q2, Q3. So that can be added together. So E equal to E1 plus E2 plus E3. So the E1 equal to 900 into AX, horizontal. E2 having two values, horizontal component and vertical component. Just now we calculated. And E3 900 AY. These two are equal. This is horizontal, this is vertical. Now we can add all. So that 1220 AX plus 1220 AY. Right? So by taking the modulus, what we got? 1725.3 voltage per meter. So the electric field intensity at the fourth corner due to the remaining three corners Q1, Q2, Q3 will be this value 1725.3 volt per meter. Welcome viewers. In this video we'll see the coordinate system. In that there are three type of coordinate system available: Cartesian coordinate, spherical coordinate and cylindrical coordinate system. First we'll see the Cartesian coordinate system. It is also called as a rectangular coordinate system. So in this coordinate system, it is represented by x, y, z. What we are drawn the graph sheet. The data are drawn in the graph x and y axis. Here we have x, y and z, three-dimensional axis available. That is, all three are length. The three parameter what we are represented as x, y, z, that is nothing but a length, right? So we'll see the diagram. So consider a point P, x, y, z in space at a distance r meter from the origin. So we have the three axes available: x axis, y axis and z axis, right? In order to represent this x, y, z, we consider one point P at a distance r meter from the origin. So this is nothing but x, y and z, representing three different points x, y and z. So corresponding this value will be z into az, that is the unit vector in z axis. The corresponding this value will be yay, unit vector in y axis. The corresponding this value will be xax, that is nothing but unit vector in x axis. So this will be very similar to the graph what we are drawn, that is xy axis. Here we have x, y and z axis. All are measured in the terms of length. So this r vector can be represented as xax plus yay and z az, right? This is not ay, is az. This ax, ay, az are the unit vectors. This xy, z is the component vector. So in this entire Cartesian coordinate or rectangular coordinate, we are representing x, y, z. This corresponding ax, ay, az are the unit vectors. Right. Now we'll see how to represent the unit vector. You know that unit vector is nothing but vector by scalar. R vector divided by r. So the r vector is nothing but x ax plus y ay plus z az. So the scalar is represented as square root of x square plus y square plus z square. So this unit vector is represented as vector by scalar. In order to represent the differential length, area and volume, we consider a point P, x, y, z. That already we considered point P, x, y, z in the rectangular coordinate system. Now we are going to increase the coordinate system by differential element. That is, we are going to increase the x by x plus dx, y by y plus dy, z is z plus dz, right? It is incremented, it is increased by the differential element dx, dy and dz, so that we can go for calculate the differential area, volume and length, right? Now we already considered point x, y, z. Now it is increased into x plus dx, y plus dy and z plus dx, right? From this, so the differential length is now from point P to point Q. So point Q is the new one by increased by differential element, right? So based on that, the differential length dl is nothing but dx ax vector plus dy ay vector plus dz az vector, right? So these are all nothing but incremental element dx, dy and dz, right? While taking modulus, it is square root of dx square plus dy square plus dz square, that we know very well. From this vector we can calculate the modulus of dl. So this is the value, right? So this is a length. We consider x, y and z. So while calculating differential area, we need to consider any two element, either xy or yz or zx, right? So first we consider dsz. So here z is there, mean dx and dy. We consider x and y that represent z axis. So dsz is dx dy into az vector, unit vector. So dsx is dy dz into ax. dsy is dz dx into ay, right? We are multiplying two parameters, x and y and z and x, right? So that because of area we need to multiply only two elements. So while going with a differential volume means length, breadth and height. So we need to multiply all three elements, dx, dy and dz, right? So in this coordinate system we represented x, y, z normal length. Then we increased into dx, dy, dz. From that we calculated the differential length, then modulus of differential length and the area by multiplying two parameters, then volume multiplying three parameters, right? So this x, y, z all are length, represented as a length, right? I will go to the second coordinate system, cylindrical coordinate system. Right? The cylindrical coordinate system represented by r, theta and z. It's not a r, it's a rho. Rho, pi and z. What is rho? Rho is the radius, that is the length. Pi is the angle, azimuthal angle. Z is the height, right? So in this cylindrical coordinate system, the two length available and one angle is available. In the previous system, all three are length parameters, right? Here we have two length available and one angle is available. If you want to represent any system with two length and one angle, we can use this cylindrical coordinate system. That's represented by rho, pi and z, right? So that we can represent the system with two length and one angle. Now we'll see the diagram. So this is x, y, z axis available. So this diagram is drawn as a cylindrical form. This is a point P. Is represented by three parameters. One is this angle, another one this length rho, another one this height z, right? So it is represented by one angle, one length rho and one height z, right? So we have rho, pi and z. It is represented by this. This point P is represented by these three parameters. Now in order to find the differential length, area and volume, we consider the differential volume element in the cylindrical coordinate system by increasing r, pi, z into dr, d pi, dz, right? In order to go for a differential volume, area and length, it is increased by the differential increment dr, d pi and dz, right? The volume element become very small. Its shape approaches that of rectangular parallelepiped and it has side the length of dr, r, d pi and dz, because dr and dz are already length, is a length component, but d pi is the angle. So in order to convert into length, it is multiplied by r into d pi. So r into d pi is equivalent to length. So this is also length, this is also length. Now pi also converted into length. D pi means angle, r d pi means equivalent length, right? Now we have three parameters, dr, r d pi and dz. From that we can easily calculate the differential length dl. Differential length is square root of dr square plus r d pi square plus dz square, right? So this is length, and this is also equivalent to length. Angle is converted into length. So while going with the differential area, it is multiplied by two parameters, r dr into d pi, dr into dz, r d pi into dz. So we are multiplying two parameters. While going with the differential volume, we can multiply all these three parameters, dr, r d pi and dz. So while volume, we are represented multiplied all three parameters, right? So in this cylindrical coordinate system, we have two length and one angle, that is represented by length and differential area and volume. Now we'll go to the third system, spherical coordinate system. So in the spherical coordinate system, what are the things available? R, theta and pi. See, this R is the length, theta and pi is the angle. So one length is available and two angles available. So in the first system, all three are length. In the second system, two length and one angle. In the third system, one length and two angle. So any system, if you want to represent either length or angle, you can choose any one of these three, either one length or two length or one angle, two angle, according to our requirement, right? So this is spherical coordinate system with radius and two angles, right? You see the diagram. Same thing, we have the x-axis, y-axis and z-axis. This point P is located in a spherical form. These lines are drawn in a spherical form. This point P is located, right? So that the distance is r. So we got one length. This angle will be theta. This angle where it is cuts here, this angle is pi, right? So the P is nothing but represented by r, theta and pi, right? One length and two angles. So this theta will vary from 0 to pi, 180 degree. But pi will vary from 0 to 2 pi, 360 degree, entire 360 degree it will vary. In order to find the differential volume, now this r, theta and pi is increased into dr, d pi and d theta, right? So the dr is already length, but d pi and d theta are the angles. So that should be represented in the in terms of length, so that this d pi is nothing but r into d pi, r into d theta. R into d theta is equivalent to the length. Similarly, this d pi is converted into r sin theta into d pi. So this also now represented as a length. So this is also length, this is also length, this is also length, right? So we cannot go with a angle. So the angle is, the equivalent angle is converted into length. D theta is r d theta. D pi is r sin theta d pi. From these three parameters, we can easily calculate the differential length, volume and area. So differential length dl is dr square, square root of dr square plus r d theta square plus r sin theta d pi square, right? So we can find the differential length, right? All three now become a length parameters. The angles, these two angles are converted into length. While going with a differential area, it is multiplied with two parameters, r dr into d pi, r dr sin theta into d pi, or r d theta r sin theta d pi. Two elements are multiplied in order to get the area, differential area. While going with a differential volume, it is dr r d pi r d theta r sin theta d pi, right? So r available two times, r square sin theta d theta d pi and dr. So here multiplied all three parameters. So in the spherical coordinate system, it is represented by r, theta and pi. One angle with one length and two angles is given by these three parameters, right? So while comparing all these three, you can able to easily understand. So in the Cartesian coordinate or a rectangular coordinate, we have x, y, z. While going with the cylindrical coordinate, rho, pi and z. While going with the cylindrical, we have r, theta and pi. So these three parameters available. So the any system according to our requirement, we can choose any one of these that will be fit to either length or two length with one angle, or one length with two angle can be selected. Now we'll see the transformation. We can convert the coordinate system from one coordinate system to another coordinate system. In order to go for the further simplification, further calculation, or further representation, we can convert from one coordinate system to another coordinate system. First we will see the Cartesian coordinate system to cylindrical. Right? Cartesian means you know that x, y, z. Suppose you are having x, y, z, three parameters are available. If you want to convert into cylindrical coordinate, that is rho, pi and z, that is possible. How will you convert this rho? Rho is nothing but square root of x square plus y square. See, by using these three parameters are represented. Right? Rho is represented as square root of x square plus y square. Pi is nothing but tan inverse y by x. Z is taken as it is. Right? So that from x, y, z Cartesian system, we can convert into cylindrical system by using this formula. Similarly, cylindrical to Cartesian, that is reversed. Cylindrical we are having rho, pi and z. From that we can convert x, y, z. How will we convert? X is nothing but rho cos pi. Y is nothing but rho sin pi. Z is taken as it is. Right? So that we are able to convert cylindrical system into Cartesian system. We can calculate this x, y, z by using this formula. Then another is Cartesian to spherical coordinate, that is x, y, z into r, theta and pi. Right? This is a Cartesian, this is spherical. How will you calculate r? So square root of x square plus y square plus z square. How will you calculate theta? Cos inverse z by r. How will you calculate pi? Tan inverse y by x. Right? So this Cartesian can be converted into spherical by using this formula. Then spherical to Cartesian, again it is reversed. Spherical is available, r, theta, pi is available. We can convert into x, y, z. Right? How will you find x? X equal to r sin theta cos pi. Y equal to r sin theta sin pi. Right? Z equal to r cos theta. So by using this formula, r, theta, pi can be converted into x, y, z. Right? So for the further simplification and further calculation, we can convert from one coordinate system to another coordinate system also. Thus equivalent formulas are available. Welcome viewers. In this video, we will see the definition of divergence, divergent theorem, Laplace and Poisson equation. First we will see the divergence. So this divergence is defined as the net outward flow of the flux. Net outward flow of the flux per unit volume over a closed incremental surface. Right? So this divergence, what is defining? Outward flow of the flux per unit volume, flow of flux over a closed incremental surface. So that is given by divergence A equal to limit del V tends to 0. The volume tends to 0. Surface integral, this is double integral, A dot ds divided by dV. So this is nothing but is a flow of flux in a surface area divided by volume. So that is a definition given. Right? Divergence A equal to limit the volume tends to 0. The surface integral of A dot ds divided by dV. Net outflow of the flux per unit surface divided by volume. Right? So this del A can be represented as del dot A. Right? This also this symbol is del. Right? So we'll go into the del operator. So it is given as the dou by dou x plus dou by dou y plus dou by dou z. It's a partial differentiation. The del operator is nothing but a partial differentiation. In that there are three types of coordinate system available. Cartesian coordinate system. If it is Cartesian coordinate system, it is dou ax by dou x, dou by dou y, dou by dou z. Right? In case of del A is given, it is partial differentiated with dou x, dou y and dou z, because in Cartesian system we have 3 parameter x, y and z. While going with a cylindrical coordinate system, the same thing what we have r, pi and z, right? R, pi and z, so that dou by dou r, dou by dou pi, dou by dou z, right? So this dou z and dou r, these two are length, but this dou pi is the angle, so that in order to make it into equivalent, it is divided by 1 by r. So this also become the length equivalent to the d pi, right? This is the length parameter, this is the length parameter. In order to make this angle into equivalent length, so that all will be equivalent length, so that it is multiplied by 1 by r. While going with a spherical coordinate system, it is represented by r, theta and pi, right? Dou by dou r, dou by dou theta, dou by dou pi. This r is the length parameter, but theta is angle, so that it is multiplied by 1 by r. Similarly, pi is also length, so it is multiplied by 1 by r sin theta, so that this will be length, this will be length, equivalent length to d theta, this will be equivalent length equivalent to d pi. So all three become a length parameter, right? So in Cartesian we have x, y, z. In cylindrical we have r, pi and z. In spherical we have r, theta and pi, right? So that we can find the del operator using any one of these coordinate system. Now we'll see the divergent theorem. From the divergent definition of divergent, we'll go to the divergent theorem. So what is given is a double integral, surface integral a dot ds equal to triple integral, volume integral del dot a into dv, right? So the divergent theorem gives relating the surface integral to volume integral, double integral to triple integral, right? What is the definition given? The line integral of the normal component of any vector field over a closed surface. So this is the line integral of the normal component of any vector field over a closed surface is equal to integral of the divergence of this vector. This is a divergence of this vector throughout the volume enclosed by that closed surface. So volume enclosed, this is a surface, this one is a volume enclosed, right? So any vector field surface integral is equal to divergence of that equivalent field in a closed volume surface, closed volume, right? Relating the surface integral to volume integral, right? This is the theorem, statement of the divergence theorem. Now we'll go to the proof of this. So in this proof, first we'll start with the divergence. The divergence of any vector A is given by, what is that? Del dot A equal to dou AX by dou X, dou AY by dou Y, dou AZ by dou Z, right? Here we are using the rectangular coordinate system, right? Del dot A, that is nothing but divergence of A. Now multiply with the volume integral, triple integral, because in the divergence theorem it is relating volume integral to surface integral. Okay, so we start with the divergence. Now we are multiply with the triple integral on both the side. So triple integral del dot A dv equal to triple integral this factor dou x, dou y, dou z. Because of triple integral we need to integrate with respect to dx, dy and dz, right? First we will consider the x direction. Consider an element of volume in x direction. Then we'll go to y and z. First we'll consider only x direction, right? So triple integral dou ax, dou x into dx, dy, dz, right? We consider only this parameter in the x direction, right? So that is equal to double integral. So this alone is written as a single integral, right? Because first we need to integrate with respect to x, then y, then z. So we are considering this. So that double integral of is inside integral dou ax by dou x into dx, dy, dz. So first we consider the x parameter. What is dou Ax by dou x into dx? These two got cancelled, only we got Ax, right? Ax into dy dz. So then what will happen? Dou Ax by dou x dx dy dz is nothing but double integral. Now this triple integral is reduced to double integral Ax dou y dy dz. So that can be written as Ax dsx. What is sx? X means y into z. The x represent the y coordinate and z coordinate, right? So this entire x direction can be represented as Ax into dsx, right? Similarly, we can go for the other is given here, where dy dz equal to dsx, that is surface area normal to the x direction, right? Now we got the value for x direction. Similarly, we can calculate y and z direction. So similar to x direction, the y also can be written as dou ay by dou y into dx dy dz can be written as the surface integral. Now that triple integral is reduced to surface integral ay dsy. Previously what we have? Ax dsx. Similarly, y means ay dsy. Similarly, for the z direction, az dsz, right? Now we got all three, ax, ay, az from equation 1. This is equation 2 and 3, right? So from all these three equation, this side is triple integral v del dot a dv equal to, so from equation 1 and 3 we can write this ax dsx plus ay dsy plus az dsz, right? We can now see this triple integral is equivalent to this double integral, surface integral, right? So the entire thing can be written as a into ds. The ds is a normal. Ds means either xy, yz or zx. So that can be written as a ds, right? So triple integral, volume integral del dot a dv is nothing but double integral a dot ds. So that is the statement given by the divergence theorem. That is, the divergence theorem converts the surface integral into volume integral, provided that closed surface encloses certain volume, right? It converts from volume integral to surface integral for a closed surface. Now we'll see Poisson and Laplace equation, right? We start from, consider a Gauss law in point form del dot d equal to rho v, right? We start from this, the expression del dot d equal to rho v. You know that d equal to epsilon e, so that replace this d as epsilon e, right? So del dot epsilon e equal to rho v. You take this equation number 1, but E equal to minus del V, another relation is available. Electric field intensity equal to negative of the potential gradient, E equal to minus del V, right? Now we substitute this E in this first equation. So del dot epsilon, here we are substituting Es minus del V equal to rho V. So what will happen? This epsilon is taken outside, minus epsilon. So del dot V equal to rho V. So that is nothing but del square V minus epsilon del square V equal to rho V, right? So that can be written as del square V equal to minus rho V by epsilon, right? After simplification, what we got? Del square V equal to minus rho V divided by epsilon. So this is nothing but a Poisson equation. This equation is represented as Poisson equation, right? In this Poisson equation, if the volume charge density is 0, that is, there is no charge is available, the rho v is 0, then it is true for dielectric medium, then this equation become Poisson equation. The Poisson equation become like this, del square v equal to 0, right? So in this above Poisson equation, if the charge is 0, that is nothing but dielectric medium. The charge is 0 means it's a dielectric medium, so that Poisson equation become del square v equal to 0. The charge is 0. So this equation is represented as a Laplace equation. Del square V equal to 0 is nothing but a Laplace equation.